In this video, we're going to look at the concept of absolute convergence. The basic idea is to consider a series summation n equals 1 to infinity a sub n. Let's look at the summation n equals 1 to infinity absolute value of an. That means we're taking the absolute value of every term. So let's expand out the series. We get absolute value of a sub 1 plus absolute value of a sub 2 plus absolute value of a sub 3 and so on. So these terms are the absolute values of a sub n of the terms an. So definition, a series summation n equals 1 to infinity a sub n is called absolutely convergent if summation n equals 1 to infinity absolute value of a sub n is convergent. Alright, let's look at an example. Here we have summation n equals 1 to infinity negative 1 to the power of n plus 1 times 1 over n squared. Let's expand out this series. Put n equals 1, negative 1 to the power of 1 plus 1, negative 1 squared is 1, so we get 1 minus 1 over 2 squared plus 1 over 3 squared minus 1 over 4 squared and so on. Now this is absolutely convergent because if we take the absolute value of every term, n equals 1 to infinity, absolute value of negative 1 to the power of n plus 1 times 1 over n squared, the absolute value gets rid of the negative signs, so we just get summation n equals 1 to infinity 1 over n squared. And this is a convergent p-series, p equals 2. P-series. It converges because p equals 2 greater than 1. Convergent. So what we have shown is summation n equals 1 to infinity absolute value of negative 1 to the power of n plus 1 divided by n squared is equal to summation n equals 1 to infinity 1 over n squared, and if we expand this is a p-series with p equals 2, so get 1 plus 1 over 2 squared plus 1 over 3 squared, 1 over 4 squared, and so on. This is a convergent p-series. Convergent p-series with p equals 2 greater than 1. So we can say that this series converges. Alright, let's look at another example. So here we have summation n equals 1 to infinity, negative 1 to the power of n plus 1 divided by root n. Let's expand out the series. Plug n equals 1, and we're going to get 1 divided by root 1. Plug n equals 2, minus 1 over root 2. And plug in n equals 3, plus 1 over root 3, minus 1 over root 4, plus, minus, and so on. This is convergent by the AST. Convergent by the alternating series test. The reason is, of course, because it's an alternating series, but most importantly, it satisfies the two conditions of the alternating series test. Namely, the terms are decreasing in magnitude, an plus 1 is less than an. Let's check this condition. 1 divided by root n plus 1 is less than 1 over root n. Because we're making the denominator larger, the ratio becomes smaller. The second condition, the limit as n approaches infinity of an is equal to 0. So the limit as n approaches infinity of 1 divided by root n is equal to 0. Both conditions of the alternating series test are satisfied. So therefore, this series is convergent by the alternating series test. However, if we do an absolute test, so if we take the absolute value of every term, n equals 1 to infinity, absolute value of negative 1 to the n plus 1, divided by root n, the absolute value gets rid of the negative signs, and we get summation n equals 1 to infinity, 1 over root n. And this is a divergent p-series. Divergent p-series with p equals 1/2 less than 1. So what we have shown is that when we take the absolute value of every term, we get summation n equals 1 to infinity, 1 divided by root n. This is equal to 1 plus 1 over root 2 plus 1 over root 3 plus 1 over root 4, and so on. And this is a divergent p-series. Divergent p-series with p equals 1/2, which is less than 1. So let's look at a definition. If summation n equals 1 to infinity absolute value of a sub n diverges, and summation n equals 1 to infinity a sub n converges, then summation n equals 1 to infinity a sub n is called conditionally convergent. And the example that we just looked at is an example of a conditionally convergent series. The reason is because the summation, if we take the absolute value of every term, so summation n equals 1 to infinity, absolute value of negative 1 to the n plus 1 divided by root n, the absolute value gets rid of the negative signs, we get summation n equals 1 to infinity 1 over root n, which is of course a divergent p-series. So when we take the absolute value of every term, the series is divergent. Divergent p-series, p equals 1/2, less than 1. However, if we apply the alternate series test, summation n equals 1 to infinity, we showed earlier that this same series actually converges by the alternating series test. The reason, of course, is because the terms decrease in magnitude and the limit of the nth term is equal to 0. So this is a convergent series by the alternating series test. For this reason, we say that this series is conditionally convergent. All right, let's look at another example. Determine if the series summation n equals 1 to infinity sine n divided by n squared is convergent or divergent. Let's expand out the series. Summation n equals 1 to infinity sine n divided by n squared. Plug n equals 1, we get sine 1 divided by 1 squared plus sine 2 divided by 2 squared plus sine 3 divided by 3 squared plus sine 4 divided by 4 squared. If you're calculating these in a calculator, please make sure that you're in radian mode, because all of calculus uses radians. Don't use the degree mode, that would give you wrong results. So this series has both positive and negative terms. If we look at sine 1 and plug this into a calculator, this is positive. Sine 1 is positive. Sine of 2 radians is also positive. Sine of 3 radians is also positive, but sine of 4 radians is negative. But it's not alternating. But it is not alternating. So we can't use the alternating series test, because to apply the alternating series test, it has to be alternating. Every pair has to be alternating. It has to be plus, minus, plus, minus, plus, minus. In this case, we have plus, 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 and then a negative. So we can't apply. Can't apply the alternating series test. So we should apply the absolute convergence test. Let's look at summation n equals 1 to infinity, absolute value of a sub n. All right, so what we have is summation n equals 1 to infinity, absolute value of sine n divided by n squared. Now n squared is always positive, so we can just write this as summation n equals 1 to infinity, absolute value of sine n divided by n squared. Now we know that absolute value of sine n is less than or equal to 1 for all n. That's because sine n is less than or equal to 1 and larger or equal to negative 1. So summation n equals 1 to infinity of absolute value of sine n divided by n squared is less than or equal to summation n equals 1 to infinity 1 divided by n squared, because absolute value of sine n is less than 1. So now we know that summation n equals 1 to infinity sine n, summation n equals 1 to infinity 1 over n squared is a convergent p-series. Why is it convergent? Because p is equal to 2 greater than 1. Convergent p-series with p equals 2 greater than 1. Now, summation n equals 1 to infinity absolute value of sine n divided by n squared also converges by the basic comparison test because it's less than a converging p series. So summation n equals 1 to infinity absolute value of sine n divided by n squared also converges by the basic comparison test. So for this reason, we can say that summation n equals 1 to infinity sine n divided by n squared is absolutely convergent. And if it's absolutely convergent, it will be a convergent series. Absolutely convergent. And therefore is convergent. So basically what this test does, the basic idea is we look at the absolute value of every term and we look at that series, and if the absolute value of every term, if the series that's made up of the absolute value of every term converges, then the original series will converge as well. So let's review some of the key concepts. If summation n equals 1 to infinity absolute value of an converges, then summation n equals 1 to infinity a sub n is absolutely convergent. Absolute convergence implies convergence. If summation n equals 1 to infinity absolute value of a sub n converges, then summation n equals 1 to infinity a sub n converges as well. Now let's look at conditional convergence. If summation n equals 1 to infinity a sub n is conditionally convergent, that means that summation n equals 1 to infinity absolute value of an diverges, but summation n equals 1 to infinity a sub n converges. So we looked at an example earlier with negative 1 to the power of n plus 1 times 1 over root n. Because when we took the absolute value, we had a divergent p-series. 1 over root n is a divergent p-series with p equals 1/2. But with the alternating series, summation n equals 1 to infinity negative 1 to the power of n plus 1 times 1 over root n, with the alternating series test, this is a convergent series. So for that reason, we called it a conditionally convergent series. All right, and lastly, if the limit as n approaches infinity of a sub n is not equal to 0, then the series diverges. That's the easiest test of all, because then we don't have to do anything after that. So if the limit of the nth term is not 0, that means at infinity, you're basically adding terms that are non-zero, so the series has no chance of converging. Much of the tests that we do, whether it's the basic comparison test, limit comparison test, integral test, ratio test that's coming up later on, all of these tests are essentially looking at what happens at infinity. It's not looking at what happens for the first few terms. All of this analysis is what's happening at infinity. And that's why we often take the limit as n approaches infinity. Because at infinity, the behavior determines the convergence or divergence of the series. So if the limit as n approaches infinity of a sub n is not equal to 0, then summation n equals 1 to infinity of an diverges. This is called a divergence test. Let's actually look at an example of that, because we didn't do this particular example. So let's look at summation n equals 1 to infinity and 2n divided by n plus 5. All right, if we take a look at the limit as n approaches infinity of a sub n, this is equal to limit as n approaches infinity of 2n divided by n plus 5. divide by the highest power in the denominator, divide by n, divide by n, divide by n, and take the limit. So we get limit, n approaches infinity, 2 divided by n over 5. Sorry, n divided by n. Let me correct this. N divided by n. So we get n over n is 1 plus 5 over n. Take the limit as n approaches infinity, 5 over n approaches 0, and the result is 2. The limit as n approaches infinity of an is equal to 2, does not equal to 0. Therefore, the series diverges. Summation n equals 1 to infinity. So essentially the summation, if you add up all the terms, it approaches infinity in this case, because we keep adding terms that are not decreasing in magnitude, and at infinity we have a term that whose value is not 0. So this diverges. This series diverges by the divergence test. All right, thanks.